Kuzangpo, welcome to Bhutan e-learning program. I am Khaganath Gajmer from Dampu Central School, Sirang. In today's lesson, I'll be discussing about chemical thermodynamics under key stage 5 for class 11 and 12. So, in today's lesson, let's look at what are the objectives that we are going to fulfill towards the end of our lesson. We'll try to define what is thermodynamics. We'll explain the system and the surrounding. We'll illustrate different types of thermodynamic processes. We'll also define internal energy and also state first law of thermodynamics. After that, we'll also do some calculations for work done. Let's look at what is chemical thermodynamics. It's the branch of chemistry which deals with various chemical and physical process that involves energy change. So, this chemical thermodynamic is basically to do with the study of energy changes that takes place during any processes. It can be chemical process or it can be physical process. First of all, let's look at what we mean by surrounding and the system. Now, system is the specific portion of the matter under study and is separated from rest of the universe. Now, if you look at this one, now if we take a solution of in this conical flask, so we are studying about this solution, so the solution becomes the system and rest outside whatever is there, it becomes the surrounding. Now, this surrounding and the system inside is separated by a boundary. So, always a system and a surrounding is separated by a boundary. Now, here the glass wall, the container, the wall of the container becomes the boundary. So, this is called system and which is separated from its surrounding by a boundary. Now, system is of different types. We have first one, open system. In open system, both mass and energy exchange can take place between the system and the surrounding. For example, if we have water inside this container, it is open. So, we can add mass as well as we can also remove mass from the system. So, there is exchange of mass between the system and the surrounding. There is also exchange of energy between the system and the surrounding. The inside this container with the water can become, if it is hot, after some time it can become cold. If it is cold, if you keep it in a warm environment, it can become warm. So, there is the exchange of both mass and energy. Next one, we have closed system. In closed system, there won't be any exchange of mass between the system and the surrounding, but there will be exchange of energy between the system and the surrounding. For example, if you take a glass of water and then close it, tightly close it with the lid, then it becomes a closed system where nothing can go in, nothing can come out, but it can have the exchange of energy between the with the surrounding. Next we have is closed isolated system. In the isolated system, both mass and the energy cannot be exchanged between the system and the surrounding. For example, if you take water in a thermos flux, if you take warm water, the water will remain warm, which means the heat has not come out into the surrounding. So, there is no exchange of energy between the system and the surrounding, as well as there is also no exchange of mass. Whatever amount of water that we take in a thermos flask, the same quantity will remain. So, this is called isolated system where there is no exchange of mass and energy between the system and the surrounding. Let us look at different types of thermodynamic processes. The thermodynamic processes, the operation which brings about the change in the state of a system are called thermodynamic processes. There are different processes which will change the system from one state to another. The first one that we have is isothermal process. In isothermal process, iso means to do with same, thermal means to do with heat, the energy. So, isothermal process, in this process, the temperature of the system will remain constant. During the process, the temperature will not change. Here, change in temperature is 0. So, examples of isothermal processes, we have boiling, freezing, we have condensation, all these processes are isothermal in nature. So, for example, if boiling takes place, boiling always takes place at a particular temperature. So, there is no change of temperature during the boiling. So, this becomes isothermal process. So, water boils at 100 degrees Celsius. How long you boil? If you boil it for 1 hour, 2 hours, then still if you look at the temperature of that particular water, boiling water, you will see that it is almost 100 degrees Celsius. So, constant temperature. Even freezing takes place at constant temperature. Even condensation takes place at constant temperature. So, these are examples of isothermal processes where temperature remains constant. Next, we have adiabatic process. Adiabatic process. In adiabatic process, there is no exchange of heat energy between the system and the surrounding. But what will happen is the temperature will change during this process. The adiabatic process is always carried out in an isolated system. We do not want the heat to come out of the system or enter into the system. So, what we do is, if adiabatic process is to be carried out, it has to be done in an isolated system. So, let us look at examples of adiabatic process. Let us look at the compression, adiabatic compression of this gas. Now, if you compress this gas, let us see what happens inside. So, process is compression. So, here the molecules are becoming in red color, indicating the heat is being generated, but heat cannot come out of the system. Therefore, the temperature inside the system will increase. Now, if we expand the gas, then what will happen? The heat will not be released now. The system will cool. Therefore, the temperature will decrease. So, whatever amount of heat is being present in the system, that much of heat will remain there. So, it will not be given to the system, surrounding, nor it can absorb heat from the surrounding. So, this is called adiabatic process, where constant heat is maintained in the system. But if process occurs in this kind of system, then there will be change in the temperature. Let us look at next isobaric process. It is a process during which the pressure of the system remains constant. Iso means same, baric means to do with the pressure. So, the process occurs at constant pressure. So, here there is no change in the pressure during the process. For example, evaporation of water at boiling point. So, at boiling point the evaporation takes place. During that time, the pressure above the liquid remains always constant. That means the boiling takes place at a constant atmospheric pressure. So, this is called isobaric process. Let us look at the expansion of gas in an open system. Let us take this one. So, what is happening is, when we heat, the volume will change, but the pressure inside remains constant. So, this is the isobaric process. Let us look at isochoric process. This is a process during which the volume of the system remains constant. So, there is no change in the volume. So, here change in volume is 0. Example, heating of substance in a non-expanding chamber. Now, if you take a chamber and then this piston does not move and you heat it, what will happen? Let us say we are heating, but we are not allowing volume to change. So, inside you will see that the temperature is increasing, at the same time the pressure also increases. That is why we are not advised to keep our cooking gas cylinder, LPG cylinder, near to any hot objects, because it has a constant volume. So, when we heat, the pressure inside will increase, and when pressure becomes too high, there is a chance that the cylinder might burst. So, this is the reason. So, that is isochoric process with no change in the volume. Let us look at cyclic process. Is the process during which the system comes back to its initial state. Now, the system, when the process takes place, the system will change from initial state to final state. Again, it will come back to the initial state. So, this kind of process is called cyclic process. For example, water cycle. Water cycle is a cyclic process that happens in the nature. Another example that we can have the cyclic process is in the refrigerator. The gases are being cycled, recycled again, and the flow of gas takes place in a cyclic manner. the cold gas comes out, and then it becomes hot outside, again inside it becomes the same gas goes into the refrigerator. So, this is a cyclic process. The system comes back to its original or initial state. Let us look at what is internal energy. Internal energy of a system. Now, internal energy is the energy stored in a substance by virtue of its chemical nature. Now, different systems will have their own energy, internal energy, the stored energy in them. So, they have their own energy, the systems will have their own energy, it is all because of the chemical, by virtue of their chemical nature. For example, we also have human beings, different individuals have different energy. It is because the difference in energy could be due to by being virtue of what we are. Different persons have different energies because of being virtue of what we are actually. So, likewise, system will also have their own energy. It is all because of the virtue of its own chemical nature. So, that is called internal energy, that is stored, the total stored energy in a system. Now, internal energy is actually the sum of translational energy, rotational energy, then we have vibrational energy, then energy of the electrons and the energy of the nucleus. If we sum it up, all these energies, then it becomes the total energy, which is called internal energy of a system. Now, in any process, when we have to calculate, we do not actually calculate internal energy as such. What we calculate is we calculate the change in internal energy. When a system changes from one state to another state, then what we do is there is a change in the energy. So, what we calculate is we calculate that particular change in energy during the process. So, change in energy, internal energy is always calculated as energy of the product minus the energy of the reactant. Now, let us look at the first law of thermodynamics. This first law of thermodynamics basically deals with the conservation of energy and also transformation of energy from one form to another. So, we can transform energy from one form to another. The energy gets transformed at a different steps, at different process. There is the exchange of energy in different forms. So, first law of thermodynamics, it states that the energy can neither be created nor it can be destroyed, but can be converted from one form to equivalent amount of another form. So, it basically says that the energy cannot be created nor it can be destroyed, but we can transform energy from one form to equivalent amount of another form. So, the universe itself is given with a constant energy. Nobody has that right to create energy, nobody has that right to destroy energy, but we can transform one form of energy into another form. But if you look at the total energy, it is always constant. It also says that the sum of all forms of energy of the universe, the whole energy of the universe, the energy of the whole universe is always constant. That means in the universe we have system and the surrounding. If we total it up, the energy of the system and the surrounding, then that total energy is always constant. It says that whenever a certain amount of energy of one form disappears, an equivalent amount of other form of energy must appear. So, if one form of energy disappears, there should be on other side, there should be another, energy reappearing in another form. So, there is no destruction, no creation of energy. It is always constant. It is not possible to construct a perpetual motion machine, that is a machine that works without consuming energy. It also says that we cannot have a machine which can move without consuming energy. If a machine is there to move, it must consume energy. That is what the first law of thermodynamics says. Now, for example, in this case, water, if we have water here, and if we have to break down this water into hydrogen and oxygen, then we need energy of, let us say, 68.4 kilocalorie. Now, if you have to reverse the process, if you have to now make water out of hydrogen and oxygen, in that case, you will have to, in that case what is happening is the energy will be released. So, back process, oxygen plus hydrogen, water will be released. Now, when we look at the energy consumed and energy released in this kind of process, it is always same. That means there is no destruction nor there is creation of energy in the process. So, energy always remains constant. Let us look at what is heat and work. Now, we know that there is exchange of energy between the system and the surrounding. Now, the exchange of heat between the system and the surrounding can take place in different forms. It can be in the form of light, it can be in the form of heat, it can be in the form of work. So, these are different ways by which the system and the surrounding can have the exchange of energy. Let us look at what is heat. So, heat is also a form of energy which is exchanged between the system and the surrounding under the difference of temperature. Now, if you look at this too, if we have a glass of, let us say, a substance which is at higher temperature, then what will happen? Outside we have high temperature, inside we have lower temperature. Let us take this as a system and this beaker outside as a surrounding. So, what will happen is there will be flow of heat from outside to inside. So, it is flowing from surrounding to system. So, the flow of heat is taking place because of difference in the temperature at 2 points which are in contact with each other. Let us look at what is work. Now, another form of energy, in another ways by which the system and surrounding can have the exchange of energy is the work. Now, work is said to be done when an object is displaced in the direction of applied force, that we already know. Now, in thermodynamics, how we calculate the work, how we define the work? Work is the mode of transfer of energy between the system and the surrounding under the difference of pressure. So, whenever there is a difference in the pressure between the system and the surrounding, the system the work is being done. So, flow of heat is due to difference in temperature, work is being done due to difference in pressure. So, heat due to difference in temperature, work due to difference in pressure. Now, let us look at the pressure volume mechanical work for isothermal reversible process in thermodynamics, how work done is being calculated. Let us take a cylinder with a gas inside it, and then we have a movable piston with the area A, and inside we have a gas with the pressure P. And the first one, let us take, we have this cylinder with the volume V1, and we allow now this gas to expand to volume 2. Now, in this case, we see that the work is being done. There is some displacement and there is certain pressure being exerted. So, we say work is being done in this case. So, how do we calculate the work done? We calculate the work done using this expression. So, work done is equal to minus P. In this case, in this expansion, what is happening is the pressure remains constant. Maybe other variables like temperature is changing. So, but the pressure is always maintained constant. So, here this minus P is the constant pressure, V2 is the final volume and V1 is the initial volume. So, work done is calculated as P minus P into change in volume. Now, it will come out to be now W work done is equal to minus P delta V. Delta V indicates change in volume, final volume minus initial volume. So, this is a work of expansion. This is the expression to calculate the work done if it is of expansion. Now, for compression we can have this one, compression, same expression as we have seen here, but what is here we are seeing here is that the V2 is lower, V2 is lower than V1, therefore, it becomes positive. So, if it is positive here, this will indicate that it is the work of compression. In both the case, the work is being done. One is work of compression, we have a negative side there, and another one is work of compression. In the first one, we have work of expansion with negative sign, work done, and here we have work of compression with positive sign of the work done. Now, if it is this for reversible process which can come back to its original state. Once the process occurs, it can come back. That is called reversible process. Now, if it is irreversible process, we use this expression to calculate the work done, where we have again change in the volume, but P2 becomes the final volume. This P2, after the process, the P2 becomes the final pressure. After the process, the pressure changes. It looks like in this case, the pressure changes. So, whatever final pressure is that we take to calculate the work done. So, these two are for reversible process, this is for irreversible process. Let's look at a simple numerical on the work done. A sample of gas is compressed at a pressure of 0.5 atm from a volume of 400 centimeter cube to 200 centimeter cube. Calculate the work done. So here it indicates that it's a work of compression. The volume is reduced from 400 centimeter cube to 200 centimeter cube. So there is a compression reduced in the volume, but that process is carried out at a constant pressure of, let's say, 0.5 atm. How do we calculate the work done? So it's all given here. Here we have pressure, constant pressure 0.5 atm, B1 400 centimeter cube. You'll have to change this one into liter. Then we have V2 200 centimeter cube, again change to liter, 0.2 liter. Then how do we calculate the work done? Work done we know is minus P V2 minus V1. So we substitute the value of P, and that's what we get here, 0.1 as the work done. But this work done is in the unit of liter atm, this liter atm. Now if you have to convert, we have to convert this one into joule. So when we have to convert this into joule, we'll have to multiply by 101.32. So when we multiply by this value, then whatever work done we get is in the form of joules. So this is the work done. So here we have positive sign indicating that it is the work of compression. So that's how we calculate the work done. Let's look at the mathematical form of first law of thermodynamics. Okay, let's say we have a cylinder of gas here, cylinder of gas with the internal energy E1. Let's say that this cylinder of gas absorbs heat Q. Now the total energy in the system will become E1 plus Q. Now after that, this system does a work, let's say expansion, and spending some of the energy that is there here. So what will be its final energy? Now it will be E1 plus Q minus W. So some amount of energy is being spent in doing the energy. So this will be the final energy of the system. So E2 is the final energy. So E2 is E1 plus Q minus W. So E2 here, this is the final energy, this is the initial energy. So in this case, what we do now, E2, if we take this side, E2 minus E1 will be now Q minus W. Now what is E2 minus E1? Delta E, change in internal energy, which is equal to Q minus W. So here delta E is the change in internal energy. Now if this is the expression delta E equals to Q minus W, so minus W here, minus negative sign here indicates is the work done by the system. Now if you have plus sign here Q plus W, this will indicate work done on the system and by the system. By the system negative, on the system positive. Work of expansion negative, work of compression positive. So that's how we calculate change in internal energy. Let's look at this question. The gas in a cylinder is allowed to expand from 1 liter to 5 liters against a constant pressure of 1.0 atm. During this process, 500 joules of heat is absorbed from the surrounding. Calculate the change in internal energy of the system. So here everything is given. Now here work done is equal to again minus P V2 minus V1. So we have pressure, constant pressure of 1 atm, final volume, initial volume. So that's what we get, work done minus 4.0 liter atmosphere. So minus indicating it's a work of expansion. Then we convert this into joule, then that's what we get as the work done, 405.28 joules is the work done. Now from here again let's calculate the internal energy. So we know internal energy is equal to Q minus W. So Q is 500 here, 500 joules of heat is absorbed, it's positive here, it should be positive, heat absorbed, minus the work done that we have calculated is 405.28. You will have to keep this one as negative only, don't take this one here, it is negative, don't take it here and then make it positive. This negative is to clearly indicate that it is work done by the system. So that's what we get as the change in internal energy. So that's how we calculate the work done, the change in internal energy of a system using first law of thermodynamics. With this, let's look at what we have done today in today's lesson. We discussed about types of system. We also discussed about thermodynamic processes, internal energy, heat and work. We also stated first law of thermodynamics. Okay, now let's look at some of the questions. You can do it on your own. Differentiate between isothermal and adiabatic process. Make a table of difference between these two terms, isothermal and adiabatic process. Using the mathematical expression of first law of thermodynamics, write the expression for adiabatic process and isochoric process. Now you have the first mathematical, you have the mathematical form of first law of thermodynamics. Using that, write what would be the expression for adiabatic and isochoric process. You will have to deduce that and then find it out. With this, thank you so much for being here. Thank you. I will see you in my next lesson of thermodynamics. Thank you.